Recording again, and I guess I'll jump right in and share my screen. So we'll get back to that poll hopefully later this evening, and but now we're going to look at how can we deal with this particularly onerous problem of vanishing gradients and exploding gradients and that type of thing, right? So we'll use this concept of gates. I'm just going to talk about this super high level. I did include kind of the original classic paper on this technology as a link, or actually I uploaded a paper in that case. So you can go and look at it. But gates are parameters that are learnable, that control when information flows through a system, and we configure them so we can forget information, and so we can learn that some information we don't want to keep hold of for really long time because it's very temporal, and we want to kind of forget that concept so that it's not affecting our present or future inferences, right? Or we might want to store it, and or we might want to update it, and we might want to just output it, right? So this gets put together into this long short-term memory cell, and where now we have xt input and yt output, but then these things can be cascaded along with each other, and we can have these activation functions, in these cases sigma, and here's tan h, and so on, and we can construct this to, again, be able to learn when certain information should be forgotten, when it should be stored and saved for later, and when information should be updated, and when it should be output. So, and all of that is all predicated on this information that's flowing through this system. Now, this was the kind of the standard approach for dealing with things like language that have this sequence to it, where you want to memorize or remember certain words that happened before. I played around with them in trying to recognize bird calls, where you might have a complex bird call and it has certain tones in it, certain chirps at certain times, and it's all related to the beginning of the call. So it's not just a bird tweeting, but it's where they have more complex calls and trying to identify those. So a couple of different applications. So it's used in audio signals and other kinds of signals, and also used in words, sentences, and that type of thing. But more recently, in 2017, there was this very classic seminal paper, very important, called "Attention is All You Need," and this has impacted a huge part of machine learning research since it has come out, and it's a big deal in terms of large language models and all sorts of different generative techniques and whatnot. So and it's important in this sequence modeling. So, and really it's a combination of several key technologies. When you actually read the kind of footnote on all these different authors, it goes and tries to explain what author did what for this overall system, and it's an amazing combination of several different key technologies. Again, we're going to take a super high level look at this. If you're taking a course, a graduate course at Manhattan College that's focused on machine learning, not higher level concept like autonomous machines, then you're likely studying this at a much deeper level. So I'm just going to introduce the concepts here real quick. So attention is something we've struggled with for a long time, and trying to replicate how humans and other mammals and whatnot are able to use attention in their sensory processing, right? So right now my eyes are pulling in all sorts of information, but somewhere in that whole sensor to brain process is my ability to focus attention onto what I am concluding is important right now, right? And but that my attention could be drawn away if I see something that warrants my change in focus, right? So attention is used to focus processing on certain parts of an image, sequence, etc., based upon, and this is the key in how we're implementing this, similarity between a query and keys, and then use that to retrieve or extract a value. Now think back to maybe your math methods course. I think you probably take that junior year, first semester junior year maybe, I'm not sure. I taught that once, but so you learned about the dot product. You probably learned about it in calculus too, right? So it's a nice convenient way of looking at how similar two vectors are, right? So the dot product projects one vector onto another. And yes, we can use that to determine an angle between them and that type of thing. But really what we're doing is that we're assigning a numerical value that shows how similar those two vectors are. And they're, it's a multiplication and addition across the different elements, right? So I hope you all remember how to do a dot product. So attention uses that, right? Because we want to see this similarity between what we're querying, what we're asking for, and some keys that we have developed, right? And it uses a scaled dot product of vectors or matrices, right? So we can expand that to matrices. Now, before I go on, I'm going to take another little detour here and play some catch up. So I've mentioned the softmax layer a few times in previous lectures, but I don't think I went into it in detail. But it is an important activation type. So if you're using Keras, TensorFlow, or something like that, it's going to show up as a layer, but really it's part of the activation and how all of that is calculated that makes it a softmax. So what we're doing is we're converting some classification data into a proper set of probabilities, right? So what do we know about probabilities? So hopefully you've had some probability theory and statistics of probability. And so we know that probabilities can't be less than 0. They can't be greater than 1. If you have a set of categories, then they should all sum to 1, right? And if you look at the, I'm not doing this in a mathematically rigorous way, I'm just talking about it, right? So if you look at the whole set of different samples that you could pull from a set, a collection, if you look at that entire set, that probability that you're going to pull something from the set is a 1, right? And stuff. So the whole thing needs to sum to 1. So we do that here. We're using in this softmax layer, we're using this exponential as an activation function, and but we're scaling it so that the outputs are normalized. So if you have, let's say, a output layer that's trying to classify between cars, bicyclists, and pedestrians, then that neural network may try to make the best assessment of what some object is in its view, and it might assign a 80% likelihood that it's a car, and 50% likelihood that it's a bicycle, and 5% likelihood that it's a pedestrian, right? So all those, if I did my math right, that adds up to 100%, or probability of 1. You might have actually a background category where it's none of the above, right? So, but this, by running it through a softmax, you'll end up with the outputs that are normalized such that each of the outputs of that layer are representing a true probability. And so again, when you're developing, you're just going to pull that layer out of the framework that you're using, TensorFlow, Keras, or PyTorch, or whatever, right? So but that's the concept. So when we're dealing with that. So the reason why I do that is because it does show up here in this attention head. So so our attention, or I guess strictly speaking, self-attention, is found by using this scaled dot product for similarity. So kind of a crude equation, and again, I'm bypassing a lot of the details here, but we have this query and these keys, and then we have the values, right? And so we're you know, if you've done a little bit of programming or studied some computer science, you might have run across data stores that are key value data stores, right? So you might have a database that includes some values, and then you retrieve those values using a key. So so we're producing these, or coming up with these queries. We're trying to find the keys that are most similar to that query, and then we're going to retrieve the value using this attention. And so this D sub k here is the size of the embedding, and that's I know kind of an abstract concept, but it's one way of thinking about it. Is if you're consuming a bunch of text, then you might encode each word as a value, and then we might want to embed it further. So this could be, you know, a large number like 512 or something like that, right? So it's really just scaling it, so it's a little bit in the weeds for this level of discussion. Up here is really our dot product. It's the Q times, this is a transpose operation here, so we're taking the Q vector and multiplying it using this, you know, basically a dot product times these keys, and then doing a softmax, and then doing the same, dotting it with this value vector, right? So then we can take those and we can concatenate them into multiple attention heads, right? So so honestly, it's not enough for you to really figure out how to implement one of these things, but the we talk about this in a way that you are, by having one attention head, we could, let's say, focus on some part of an image, and it might be a crosswalk, right? You've identified by the lane markings a crosswalk, right? But you might also need to be paying attention to a pedestrian, right? And so now we're going to have multiple of these attention heads, and we're going to concatenate them, and so be able to focus on multiple or several different regions of the image or sequence, right? So and then we take this and we put it all together in units. So we're cascading all these things for this overall transformer model. So again, when I first introduced this, I talked about how there's all these different authors that contributed some aspect to this big paper, and so part of that was the attention head. Part of it was this concept of using a dot product and these QKV type values, and then concatenating into multiple attention head, and then taking all of that and putting that into a transformer model. So putting this out there to kind of show you how complex it gets. But here's now your multiple attention head, and we can skip over some data flow and or process it through these concatenated multi-attention heads, and then add and normalize it, go through a feed forward network. So this would be more of a conventional neural network, right? Feed forward some number of layers and that type of thing. And then again, we've got the skip connection, so we can skip over that and normalize it. Then so all this would come from our inputs down here. It goes through some input embedding. That's basically kind of taking our inputs, whatever they are, words or signals or images or something like that, and encoding it or embedding it so it's ready for consumption in here, right? And again, I recognize I'm hand waving through this just because we could spend several lectures on this alone, right? But then we also have this positional encoding. So we need to encode the relative positions of these informations with each other, right? So this might be a bunch of inputs, but remember, in a sequence, we want some understanding of the order in which things come through. So that's what this positional encoding is doing. The combination of these two things, and they're additive in this, right? So there's a bunch of values here, there's a bunch of values there, and they're added together. Seems weird, maybe non-intuitive, but we're taking values that are encoded, and then the positioning of those, and we're adding these together. This is the dimension of this is at DK that we had back here, if you're curious. But again, that's kind of into the weeds. So then this is our inputs, but then we send that over and send that into another multi-head attention system with some outputs, where now we're going to shift our outputs to the right each time. So we got output probabilities out here that's ultimately going through this softmax layer, so we get these probabilities, and also this is this transformer model that is in turn based upon these multi-head attentions, which are concatenated versions of these inputs. So all sorts of different technologies put together to produce this transformer model. All right, so boom, I'm going to kind of leave that there, but maybe I'll talk about it a little bit in that these whether it's LSTMs or these attention-based transformers, these are producing this ability to model and predict sequence type information, right? So trajectories, signals, all words, sentences, basically. Excuse me. These are all examples of sequences that we want to process, right? It can be a sequence of frames of image captures that we're pulling off of our cameras on our vehicles, or it could be frames from our information processed out of our FMCW radar or our LiDAR or that type of thing, right? So then so I can stop sharing for a moment as I yak on here. So these are all different techniques that we can consume these sequences and then predict things, right? So again, that could be a one-to-many, a many-to-one, or a many-to-many. In this present case, we're trying to consume some, let's say, number of frames from a camera or a set of cameras. Maybe one's facing forward and one's kind of maybe at an angle or to the side or something like that, right? And so we're wanting to process multiple frames and pick up features in those frames and then predict where important things are going to be, right? So you can see where attention can be important there, right? Because it can help us understand what we're looking at, what we should be focusing on, and then tracking that from one frame to another and be able to predict where vehicle or bicyclist or pedestrian or whatever is going to be by extrapolating out that trajectory. So we're trying to solve for an output, a trajectory. And these are the two approaches to sequence modeling that have had kind of the most success. Obviously, when you do, these big classic important papers, then there tends to be a whole flurry of papers for years afterwards that are fine-tuning and adding little additions to it and that type of thing, right? So that's the big concept that I want you to come away from. If you want to dive into any of those and part of your personal research, then that's your jumping off point. But the idea is we can now use these recurrent neural nets to be able to predict trajectories. Then our further stages in that system, in the autonomous vehicle system, we'll look at do we need to update our behavior based upon this projected trajectory, right? So if we're seeing a pedestrian or bicyclist that looks like it's about to cross into our travel lane, then we need to make decisions, right? Or if we see vehicles coming up to behind us from the left, that helps us make a decision whether we can lane change or not, or whether we need to stay in our current lane, balanced by what we're predicting the trajectory of the vehicle ahead of us, right? So all these things are there to kind of set up that initial trajectories of multiple objects that we can feed into our behavior models. Okay, so we're going to shift gears a little bit now and talk about routing. Now, again, there's just lots of material to cover in this course. So let's think about routing, right? So we have some inputs, current location of our ego vehicle, and that's going to be derived from our localization module. And then where do we want to go? Well, at the high level, that's going to be our destination, and generally that's obtained from the user input. You get into a robo-taxi, you've communicated with that robo-taxi where you want to go, right? So then the objective is to determine the lane-by-lane sequence to best navigate from the current location to the destination, and then provide this information to other modules so they can make it happen. Right? So this is kind of a high-level executive. It's deciding, do we want to take the toll road or surface streets or some other highway or something to get to that destination, but that we need to do it in a lane by lane or even lane segment by lane segment type of sequence. So this is similar to how popular consumer map apps work, but generally requires higher fidelity maps. So here's that question: what might be required beyond consumer map routing? So let me see if I can take a look at. Oh, we got 6 responses. That's not bad. So yeah, so we're gonna. Let's see, response to real-time data, safety, and sensor fusion, among other things, should be required of the routing system beyond consumer map routing. The routing system should be able to plan optimal and efficient paths, taking into account factors like fuel efficiency and battery life. The routing system would require obstacle detection and avoidance outside of the normal case, right? Because normally we'd have a human handling that level of routing, and that human is using his or her sensory perceptions and then controlling the vehicle. But we need to do that in this case. So here the student produced this example. If there's construction on some road, the UAV must be able to take that into consideration and be able to reroute to another route. So be able to recognize patterns and adapt to different environments. So very good. I skipped over a few here, but okay. So good thought exercise. Thanks for putting that work in. Again, it's for you really to think about what some of these things might need to handle. So again, this diagram is from your book here, and why is it giving me that? There we go. Let's go back. All right, so here we've got some different lanes and different intersections, ways to turn, that type of thing. If we want to get over here, well, we're starting up here, then we're planning this routing using this lane by lane or lane segment type of routing. And so there might be other ways of achieving that, right? So I'm not sure if we can get to this lane here. It looks like they don't have a crossing right here, but let's say we did, then we could take this type of route. Again, there's no real crossing right there. But you can imagine that there's more than one ways of getting there. We might want to be in different lanes and that type of thing, right? So we're trying to get down to that level. So there are a few different ways of attacking this, but we're most routing is based in one way or another on what we call a weighted directed graph search under some optimization. So what do we mean by this? A graph is a connection of nodes. Let's see, maybe I could draw that in a little bit. So we might have a city here. We'll call this New York City, and then we'll have a city over here, and we'll call this St. Louis. And oh, this is terribly not to scale, but this might be Columbus, Ohio. This might be Pittsburgh here, or this might be Cleveland up here. And so sometimes when I go this direction, but other times when I drive, I go up through Cleveland and come across on I-80, and it's just a prettier drive, lots more trucks, but a nicer drive once you get into Pennsylvania, right? So these nodes here are different routing points, right? So we might travel through some of these things, right? And each one of these connections is an edge, and we call these weighted because these might be weighted with the distance, right? So and this distance here might be 150 miles. I don't know why my pen's not working very well. And this might be 250 miles up here. So that's 400, but this might be 380 here. So we can look at these and decide by looking at these weights what the best way of getting to our destination is. Now we call this a weighted graph because we're applying some weights to all these different segments or edges, as we call them in graph theory. It's directed because we're going in a particular direction. We're not, it's maybe different to go this direction than it is to go the other direction, right? So now we're going to try to search this graph under some optimization. And this is, I think, one of your questions. I just kind of rattle off minimum time, distance, energy, tolls, safest, which is one of the things that I think your book talks about, and that maybe you want to weight straight line segments with the lowest weight, and right-hand turns with maybe a little bit higher weight because maybe they're a little bit more dangerous or complicated. You might have to wait for pedestrians to clear or that type of thing, right? And left-hand turns might have an even higher weight to them because you might have to wait for traffic and pedestrians, right? So, and generally left-hand turns are a little bit more risky type of movement. So your book talks about assigning weights in those different ways, and so maybe if you can find a route that favors right-hand turns versus left-hand turns, you're going to be better off, right? So let's take a quick look. I guess I want to keep meditations. I don't know why, but what's some of our other things weighting based on safety, cost, time, distance, energy consumption, terrain, wind conditions, vehicle efficiency, traffic, efficiency in gas. Very good, very good. Energy, tolls, safety, time, distance. Maybe someone downloaded my presentation after I uploaded it because that's very similar to mine. So that's a very extensive one. But load balancing, accounting for construction, societal impacts like noise, air pollution. Very, very good. Very good. All right. So you can see that the idea, and we're going to come back to this, is that assigning these weights is a lot of the problem. We ultimately need to execute the search, and we're going to talk about a couple of different ways of doing that, but it's trying to figure out these weights that might be quite complex. So two different approaches that your book talks about, and these are again very classic. You can see that these go back way in the past, 1950s, kind of later 50s, when it was first developed, and then a few years later he published it. This Dijkstra is very, very famous in computer science world, and this finds the shortest path between two given nodes. Given those weights, using this Dijkstra algorithm will find the shortest path. But this A star, developed by these folks at SRI Institute, will possibly do it faster, fewer steps, but we need some sort of heuristics, right? And so then there's lots of other variations and that type of thing. There's a whole bunch of these things, right? But Dijkstra and A star are classic enough that once you've learned those, then it's pretty easy to learn all of the others associated with it. So let's look at this, right? So first you want to define your problem. What are you trying to route? What is important to you in this type of routing problem, right? And then you need to determine the cost or weights on each lane segment. And then you want to choose the algorithm to search for the minimum cost to get to the destination. So again, we've got a couple algorithms, many more. They're good, better, and best, maybe. I don't know. But the kind of tough part, or the thing that may make your solution better than your competitor's solution or something like that, is kind of this assignment of weights on each lane and properly defining your problem. So Dijkstra, again, as I said, finds the shortest path on a weighted graph. Graph is composed of nodes or vertices, and edges or paths that connect them. And we're going to maintain unvisited and a visited sets. Sometimes these are called open and closed for various reasons. Edge weights represent the cost, for example, distance, time, difficulty, risk, whatever. Weights must be non-negative. Right? So you're not going to get paid to take a certain road segment. The algorithm's not going to find the best route if there are negative weights involved, right? So, and yeah, if you're really looking to implement this, you're going to use some sort of priority queue for both of these to be able to implement these the fastest. So all right, so we'll walk through this, and then that'll wrap up our lecture for tonight. Maybe I'll finish early again. So I have laid out these A, B, C, D, E, F nodes, and we're going to try to get from A to F. Right now, when we're starting, we're here, and we don't know how to get to F. Right, so we're going to initialize the cost of A to 0, and the cost of all of these other nodes, the cost to get there, to be infinity. Right, so I've got these in the cost to get to these nodes are infinity, and we're going to build this little table here of these vertices, and we're going to maintain this unvisited set. And instead of having an unvisited and a visited set, I'm just going to do a strike through on the nodes that we have visited. So we're taking them out of the unvisited set. So since we're starting at A, it costs us nothing to get to A, right? So the cost is 0. And since we started at A, we've already visited it. So we can strike that out right away. Since we're starting at A, we do not have a previous node that we had to visit in order to get to A. We just started there. Right? So then we're going to update cost for the connected nodes. What nodes are connected to A? Well, that's B and C. We examine the weights on these edges or these paths, and that's the cost it takes us to get to B from A. So we assign a 1.9 there, and we assign a 1.8 as a cost to get to C. and we fill that in on the table, right? So it takes us 1.9 to get to B, and we got to B from A. Right? We still haven't visited any other nodes yet, though. So let's do that. Let's visit the lowest cost node. So we look down here, and that was C. C had 1.8. B had slightly higher cost at 1.9. I actually went through and kind of measured all these after I drew it out. And so in this case, the lowest cost node is C. So then we update our cost. What is our nodes connected to C? Well, there's A. Well, it's a directed graph, so we're not getting to A from C because the arrow is going this direction. But we can get to B at a cost of 3. But to get to B in this path would be 3 plus 1.8. That would be 4.8. The cost to get to B from A through C would be 4.8. Well, we know that it's 1.9 to go directly. So why would we take the scenic route? No, that's not going to happen. So if we valued scenery, then our weights would incorporate that, right? So we're going to leave B alone. We're not going to change that value. But another node that's connected to C is D. And it takes us 1.6 to get from C to D. But it took us 1.8 to get from A to C, so that's 3.4 as a total. So we mark that on our graph, and we put that down in our table, and we note that to get to D, we got there from C. There might be other ways to get to D, but that's the way that we've explored to date, and is the lowest cost way to date that we've done. Right? So we only update cost if it's smaller. Well, since we initialize things to infinity, almost anything, as long as it's not infinity, is going to be smaller, right? For that initial update. But then we see we did not update B immediately because our cost to go through A to C to B was still higher, right? So now we've visited C and we've analyzed it, so we mark that one as visited. Now we repeat with the closest unvisited node, B. Right, so B's the closest unvisited node, so we're going to visit that and look at what's connected to that. Well, E and D and C, so are all connected to B, right? So the cost to get to C from B would be 1.9 plus 3.0. So this directed line, directed edge down here. So 4.9. Well, it only costs 1.8 to get to A to C, so we leave that one alone. Then let's look at D. That would be 3.1 plus 1.9. for 5, right? So it costs us 5 to get to D, but this 3.4 is still lower, so we'll leave that one alone. But it will cost us to get to E. Well, that one was infinity, so now certainly this one's going to be smaller, so it's 1.8 plus 0.9 or 2.8 to get to E. Right, so we update that and we put in the previous node B there, right? So, and we mark B as being visited. So then we, process with the closest unvisited node. So we look around and we see that E has the lowest value. So both D and E have been unvisited, but E has lower value of that, of D. F, before we do this, while we're still choosing the node, is still at infinity, right? So we have 2.8, 3.4, and infinity for our set of unvisited nodes. So E is the closest one. So now we can really only get to F from E, but that's where we want to go. So that's good. So now that's how much is that going to cost us? That's 2.8 plus 1.1 or 3.9. And so we got to F using 3.9, and our previous is E. So we can mark E as visited, and we're done, right? So the lowest cost node at this point, unvisited node, is F. What is it? Maybe D. So you should still consider D here, and that would be a 5.4. So I kind of skipped that. So D technically is still the lowest cost node. It's a little bit lower cost than F. So we should see, is there a way to get from maybe A to C to D to F cheaper than this route? But no, it's not. It's 5.4, which is larger than 3.9. So we're done. We found F, and so we are, that's a typo. We're finished searching. Now we need to determine the path, though. So now we traverse the previous list and then reverse it to find the shortest path. So step one is to traverse the list. So it's F to E, E to B, B to A, right? F, E, B, A. But then that's how we might get back to A, but we want to get to A to F. So we reverse that list, and A, B, E, F. So, and then it costs us, well, I should have updated that infinity right there, but it costs us 3.9 to get there. All right, so that's Dijkstra's algorithm. Sometimes you'll see this in like computer science type, learning tutorials, YouTube videos or whatever, and they'll have a big maze and like a mouse trying to get through some maze, and it has to move one block at a time, type of thing, and you're trying to figure out what is the best way of getting to the destination. This is using gaming, a lot of video games and that type of thing, but it's a classic algorithm that has wide. It's a very generic algorithm that has a lot of applicability, but the idea is that it's able to search for the minimum cost way to get from A to F over a weighted graph. So if you think about it, Facebook and LinkedIn are graph type databases, right? Maybe you can figure out a weighting on those, and then you can figure out how to get from one contact to another, right? So just tossing that out as yet another application of these type of algorithms. All right, so can we do better? Well, Dijkstra will find the shortest, but it may take a long time to find it while exploring paths that may be short but don't make good progress towards the destination. So depending upon how it's all constructed, the problem that you're trying to solve, in our case, which roads go where and how far out of the way and that type of thing. Do you end up with some dead ends and whatnot? So a star can speed up the process by using a heuristic to estimate the costs remaining from a current node straight to the destination. Okay, so as you start the process, you might be many nodes away, but we're going to look at, try to estimate that heuristic of the cost from that current node directly to the destination. In other words, a straight line distance. Well, we can't always take a straight line distance, right? Might be mountains in the way or buildings in the way. Most of our roads are kind of on somewhat of a rectangular grid, so it's hard to take the diagonal at times, right? That might be the straight line distance, but we can't do that. So it's just a heuristic. It's not necessarily the solution. So we can look at this mathematically, where this f of n now is our total estimated cost at this step n. And we have this G is the cost to get to that point, right? Or n is the next node. This G of n is the cost to get to that next node. And H of n then is heuristic estimating the cost to get directly to the destination. So now, and then we use this as a metric when we're calculating that table, right? So we just went through that kind of step-by-step comparison, looking at the different ways to move through that graph. We did that with Dijkstra. Now we're just going to make this a little bit of update in that we're going to use this H of n as a heuristic to try to get there faster when we are doing these calculations. So this is guaranteed to find the shortest path. But if, I probably should have if and only if there, I think, I'm not exactly sure, but H of n is admissible, right? So what does that mean? Well, here I tell you, it does not overestimate the cost, right? So it's a heuristic, so it's an estimate, an easy to calculate estimate of the cost, but we want to make sure it doesn't overestimate the cost. Well, if we can calculate the straight line distance from this next node n directly to our destination, we know from high school geometry that the shortest distance between 2 points is a straight line, right? So if we use the straight, as the crow flies type distance for H of n, then it will be admissible. And in that case, it will be guaranteed to find the shortest path. So this also benefits from a priority queue in case you're interested in implementing it, right? So we begin very similarly to Dijkstra. We have this open, I'm going to call it open set this time. There's some subtleties in this one. And we're going to start at A, but I've already kind of jumped down and evaluated B and C, right? So now I've got, but I've got to still have infinity on these others. These blues numbers are my heuristic that specifies a distance from the current node directly to F, right? So I literally took a line and measured in PowerPoint. I measured the distance from the center of this node to the center of that node, this one to that one, this one to that one, this one to that one, and this one to that one. And that's what all of these blue numbers represent. All right. And so here we've gotten to this state. Now in Dijkstra, we would next evaluate C because it has the lowest cost, the nearest lowest cost unvisited node. But we're going to apply the heuristic to find out what we really believe the lowest cost node to visit is, right? So we're going to take B here is 1.9 to get to there. It turns out it's just coincidence, but it's the same distance from here to there. So it's 1.9 to get to B plus the heuristic to jump directly to F, our destination. So that's 3.8. But we also calculate that for C. So it took 1.8 to get to C, and then it's 2.8 to jump directly from C straight across to F. So that's 4.6. Well, B is lower. 3.8 is lower than 4.6. Note, in Dijkstra, we would be comparing these two numbers here. But grab my laser pointer. So we'd be evaluating these two numbers in Dijkstra, and you see we would check C first. But here we're evaluating these two numbers, and it turns out that B is a little bit closer. So we're going to mark B as visited, and now we're going to do our same thing. B is connected to, well, it's connected to C, D, and E. So we'll update those, and then we'll repeat again. We'll again look at all these unvisited nodes, and but add in this heuristic to get to our destination. So C is the same. D, it took us 5 to get to D from B, and then it will take us another 2 to get to F, right? So that'll be a 7. Now note that it would be cheaper overall to go that direction, right? To go from A to C to D to F, even though it's not fully the optimal. But so we're coming up with this cost of 7, but it's still going to work out, right? E now has this cost of well, it took us 2.8 to get to E, and it's going to cost us 1.1 to get to F. Now you'll notice we get to this point is on these ones that are connected very close or directly to F, I'm using these same numbers, right? So, but this path might meander around still, right? It might have to go around a mountain type of thing. So this could still be larger than these numbers here, right? So in this case, they're the same because I'm just pretending that these are directly straight lines. All right, so we still have E as the smallest one, and so we're going to evaluate E, and then we'll take E. Actually, we'll add this number this time, and it's still the same, so it's 3.9, and we mark off E as visited, and then we can observe that we've reached our goal state destination. But let's go ahead and finish out and check anyway. So let's do one more step here and calculate our new things from our metrics. So C again is 4.6, D is still 7, F. Well, how much does it cost us to get to F? Well, it costs us 3.9 to get from A to F, and then it costs us 0 to get to F, right? So so we're there, right? But 3.9. Now we compare all these others, and it's still smaller, right? So that means that we have found the quickest route, right? So this number here represents the optimal route from A to F. It could be that this complex in a system or something that maybe another one of these routes would have shown up. But then we do the same thing, and we would traverse this set back. So we go F to E, E to B, B to A, right? And then we reverse that. So A, B, E, F. And so I've highlighted that path there. So now note that we avoided visiting C in the A star algorithm and therefore reached the best path one step faster, right? So in the Dijkstra approach, we kind of wasted time calculating that C, and visiting C and calculating all those things, right? So it's a little bit of a trivial toy example that I came up with, but the advantage can be more significant, particularly on large-scale maps. Now, what do we need? We need this ability to estimate this heuristic, and that heuristic has to be admissible. So if we know like the longitude and latitude, and most mapping databases will do what's called a geocode. You can plug in an address, and it can look up that address and return you back a latitude and longitude. And so if you know your starting location, you plug in an address, you can retrieve that from the database and this geocoding operation. You can retrieve the destination latitude and longitude. Then, it's a trivial matter to calculate the direct distance. Well, trivial if you make some assumptions, and a little bit less trivial if it's a long distance and you need to take the Great Circle route around the globe. But kind of beyond the scope of this discussion. So now, if it's not consistent, then we need to add nodes back to the open set when replacing them with a lower cost one. So that's a little bit of kind of a nitpicking thing, but that's where if we're have visited a node and think that that's the lowest cost one, but then we do, and we visited, but then we take that out, but then we replace that node with the lower cost one later on, then we need to put it back into the open set. Kind of a nitpicky thing there. So Dijkstra and A star are these classic generic graph surf algorithms in computer science with many other options that might have advantages in different circumstances, right? So there's lots of other variations on these and other types of algorithms, but the idea is that we are building this graph of different nodes, right? So we need some sort of mapping database that includes all these lane segments, and they have to be connected in a way in this graph. And then we need to determine what kind of weights are we going to put on them, right? And then we can search that graph using some algorithm to be able to find the best way of getting there, given the way we assign those weights, right? So we kind of already dealt with this question here. So I'll note that there are ways that maybe part of the graph can be pre-calculated. There are challenges, and if you're taking a long trip, of bringing in all the different lane segments. And so let me stop sharing. And so we don't always use these directly. So so if there's a lot of lane segments, we may run out of memory to bring them all in and calculate that graph all at the same time. So we might need to bring in a little bit, try to find a route, and if we do, great, then we'll hope that's the best one. If we don't find a route, then maybe we have to bring in more different lane segments and consider maybe we have to detour around farther to get to our route than we thought originally. This all depends on how memory constrained our system is. As we're traveling, we may run into some unexpected construction or travel delays, right? So here's an example. On my Tesla, I pay an extra little bit per month, so I get traffic routing, right? So Elon gets a little bit more money out of me. And so so as I'm doing a trip, it is getting real-time traffic information and road updates and that type of thing, and will be able to reroute me. So at part of that routing system in your autonomous vehicle is going to be able to detect when a route is not feasible, and then reroute it, right? So, or detect if there's an event that may mean it's beneficial to reroute, then it'll do that again. And again, when we're doing this, when I'm driving and I see, that I'm supposed to take a right-hand turn up, take an exit onto a different interstate or something like that, I'm looking at the road signs, I'm looking at the street markings, lane markings, and I'm figuring out which lane do I need to be in order to get to that right exit ramp and that type of thing. Most of these things will, even your Google Maps or Apple Maps from your phone will tell you it's a left exit versus a right exit and that type of thing. But when we're in an autonomous vehicle, we need to narrow that down so that the vehicle isn't has some ability to know exactly which lane that they're going to be in. All right, so we'll pick up next week and show how these things tie together, looking at that kind of behavioral block where we're deciding kind of at the high level how we want to behave and make decisions based upon our traffic trajectories and our routing information, and then how that plays into our motion planning, and then touch a little bit on how that then gets implemented as a feedback control system. And hopefully we'll get started on reinforcement learning and spend a little time on that. In the meantime, I will, so those of you that submitted your research reviews, you should have gotten feedback on those and an associated grade. Recognize that I expect feedback to be incorporated for your subsequent reviews, so that as you go through, if I still see that you didn't properly give me a good citation, well, I'm going to take a lot of points off in the future. I may have taken off a few points in this first one, but I'll be intending to hold you to a higher standard as you continue on. So I'll be putting up assignments for the rest of the semester. And again, undergrads in the 449 course, I guess it is, are doing 5 papers total. So now you only have 4 more to go. And graduate students, though, are doing 10. So yeah, hopefully you've got a few. I know I've gotten a couple from people and already, but I'll put up assignments for those. And if you're undergraduate and you see 9 more assignments to submit to, just recognize that you only have to submit 4 more. Okay, but the graduate students are doing 10 papers. And I already gave you feedback when you originally did your proposal for these research reviews on your paper selections. But then as you go through this, I really want to emphasize that you want to do really research articles, right? That's my hope and expectation for you as you do this. And let me qualify that further. Original research articles. So the surveys that a lot of you did for this assignment, that's awesome. But now going forward, try to pick articles that are more involved in original research. What you're going to find is that they'll probably be a little bit more narrowly focused, but going to a lot more depth. So there's going to be some rigor that you might have struggled with to get through. We're all there, right? So when we start looking at a new field, there's some challenges in digging deep on that. The other thing I'm going to do, and I've been trying to think of how to do this, and I know I'm a little bit behind, I think, on the projects. Hopefully you're not behind, but I will put up an assignment, and basically it's going to be either meet with me next week during my regular office hours or schedule some office hours on Monday, Tuesday, Thursday, or Friday. And briefly present to me where you are at in your project, if that makes sense, right? If it makes sense to show me some software running in real time or something, that'd be great. I'd love to see that, and give you feedback and that type of thing, but also help us, have confidence that you're making progress towards the solution. If that's not going to work for you, it doesn't make sense based upon your project, that type of thing, then submit a paragraph or two stating what you've done so far, kind of, as I've said before, a little activities and accomplishments, problems and plans, right? So, and then we'll try to do this maybe every couple of weeks through the rest of the semester. Don't wait for me, though. If you're having problems, please get with me, right? I expect to be able to, help you with these things. And again, if you have some hardware, I did drop off some hardware, and I was going to have it set up so you could pick it up from Bobby, and I have a checkout sheet and have something that you signed to swear that you would return the property back to me or to the school as appropriate. I haven't really gotten any feedback. I think I had one person take me up on some hardware, maybe two people. So I haven't prioritized that. But if you do need hardware, something like that, let me know, and we can make that happen. So otherwise, any questions, any comments, sarcastic remarks, anything? No? Okay. Well, I will give you back 4 minutes of your life that you don't have to stick around anymore. And we'll see you next week.
Thank you.
Thank you.
Thank you, Professor. Have a good night.